Yeah, much better. This is our car. Yeah, the Ferrari. So first, there was a decision that we need to go virtualized. And also environment dependency and the flexible platform must be pretty much the same for all of the companies or resources. Backward compatibility was one of our special requirements because the original plan was that every single solution we have or the customers have and the applications we have should be easily moved with just a tiny amount of changes or without changes to our platform. And high and deterministic performance, this is one of our keys that is we're going to cover more. High availability and robustness, they are also from the telco area. We definitely must provide these. And finally, we try to achieve it with intact DPDK libraries. Okay, a couple of words. Virtualization, no explanation. Environment independency. We have our own chassis with our own type of cards, and we want our applications run on those. But the world moves towards the clouds, so we would like also support cloud. And it's not enough that we're just moving to the cloud. We try to expand the requirements towards our applications. So we did not try to stitch to one single hypervisor, but we try to support many. And we also want to run on bare metal. This is good for embedded systems and also much more easier to bring up just unit test environments. And as a telco company, we have many blades already deployed, and we would like to reuse them. Flexibility. It not only means that we go virtualized, but we also want to have a pretty easily configurable environment. This requirement basically came from optimization efforts because it looks like if you try to optimize something to a given hardware or a given environment, it becomes better and better. But if we try to make it more and more generic, performance just goes down. And we have a sort of a good solution. This is really a good trade-off. We're going to talk about later. Multiple application model. It means that we're processing packets. And by examining what happens, but just doing some profiling job with the packets, it turns out that some applications require different type of resources, and they have different type of bottlenecks on the very same hardware. And with just simple configuration, we wanted to support multiple different types of applications. And scalability. Again, if we have just a tiny hardware or a tiny virtual machine, we'd like to make the application run on them. And if we support a giant VM, we also want the application to run there. Of course, it requires some flexibility from the application itself. But in our typical applications, it can be solved. And performance tuning. Basically, our environment provides a pretty good approach of reconfiguring the application without recompiling it. So we're trying to play around with different configuration, just easily restarting the application, reconfiguring, restarting again, and do the profiling. And still, without hard coding anything. Backward compatibility. I was talking about one of the most important for us in the telco. The measurement is the high throughput, the packet rate. That's clear. But it's also really important to have the low packet delay variation. And it looks like there are also some optimizations in case of a Zen hypervisor that if you restart a VM, probably it will not bring back the very same resources in terms of memory if you restart it immediately, because they also came up with some solution that while one VM just goes down, the other could come up instantly. Per instance performance. This is one of our keys because basically in our environment, we use many processes and they are pretty much the same, very same. They do the same job. And this is good for scalability because it means that if you have more resources, we can bring up more processes. But it also requires that every single process could use the very same type and very same quality of the resources. equally distributed resources, again for supporting something like multiprocessing. High availability, it's again from us, from the telco. Fast recovery means that we don't have the luxury of killing a whole VM. We can just kill, we can let one process to die and just immediately bring it back, probably passing the core generation and every other tasks to another process. We try to avoid the single point of failure. It's like using the primary process. Basically, we don't use the primary process as it is now in the DPDK because we made the primary role just going between the processes. Redundancy, we're still talking about within a VM, so we don't support the redundancy as two separate VMs, 1+1 or something. This is just within the VM, so we can provide resources for redundant processes. And unlike DPDK, we try to separate the memory. This is going to be important also in terms of the robustness and also in performance. Multiprocess support. As I said, our applications typically use many similar processes, and we had to increase a bit, enhance DPDK's multiprocess support. Also, debuggability is for robustness. In some cases, for the data structures and the databases, we have chosen the guidance was from the debuggability, because in our case, we are not only supporting one single application, but we need to support many. And the important thing, again, intact DPDK common libraries. It means that, for instance, from DPDK 1.2 to 1.3, it took only 2 days for us to upgrade, and even we could do it with 1.6, or even right now with 1.7. And now, the typical applications, most of them are using really big footprint of the memory, and they really do random accesses, read and writes there. And just to keep everything work as it was before, we need to support the giant virtual machines. So we're talking about even 4-socket systems with one single virtual machine. And Xen at the moment does not provide NUMA information within the VM, so we had to come up with some solution to make our applications make use of all the NUMA resources, even if they are unaware of the NUMA. So finally, we extended DPDK with some sort of virtualizing it, but I wouldn't use the word virtualization. And now, please welcome Laszlo.
Okay, so is it? It works, okay. Yeah, so actually we finally, our main goal was to put something on top of DPDK, and that's how we started. So we have not contributed to DPDK org yet. And actually at the end, so this was our goal, and due to this we wanted to do so actually, finally, we came to the conclusion that we ended up virtualizing DPDK itself, and that was because we wanted to put something on top of DPDK. So what we did and how we did that. So actually, we split the DPDK's environment abstraction layer into two, publisher and a consumer. So it's like, oh, it's going back. So yeah, so we did decouple the environment detection layer of DPDK. So it's like currently it has it supports BSD and Linux, and on our part the consumer is the one which is reading the Linux interfaces, and the publisher is something which is publishing something to another database. Actually, we're using the X attribute tree for now to. So it's just like directory structures and a tree structure, and that's how we publish the information like the CPU, memory, and device topology into this database. And then the ELs other part is using, it's just reading from this database. And also memory configuration, so it's like the topology, the memory configuration topology as well as all the other configuration. We'll talk about that later. So device publishing, we made a kind of register, so we can register DPDK ports for certain devices. So it's like you can get the DPDK port ID 5 for a given device if you need. And yeah, selective memory mapping. So that's what Andras was also talking about. This is the multiprocess support. So it's like we can selectively map memories into the process's address space. So it's like there could be multiple processes, but one process might want just to get its private memory, which could even be a packet buffer. And so we only map the packet buffers or the memories used by a single process and not mapping everything. We'll have some slide later. So yeah, memory access control. So it's also important to not to map something, or not to map everything as read-write. So we want to map certain areas just as read-only. Okay, so this is how it looks like. So actually, at the moment with the current DPDK, it maps everything in a multiprocess address space. So it's like everything is read-write. And then what we did is that we can selectively map certain areas. So it's like these yellow marks are the read-only mappings, which every process wants to attach to, like the forwarding tables. And there are some private areas which only a single instance can access, or a controller piece. So it doesn't mean that no other processes can get access to it. So it's like everyone sees its own private, but maybe before these processes came up, another process already set up that private memory for them. Or it may be memory which was before the process died and then it came back again.
Doesn't that depend on the process type, whether it's primary or secondary? Like in the primary, it's all the primary processes are shared and the secondary processes are private.
Yeah, actually, it's as Andras already mentioned, we modified a bit these roles. So it's like you can pass the primary role. So any process can be the primary process. So it's like, but it doesn't matter. We have a flexible configuration to configure all these memories. We will hopefully have time to show that. So yeah, so we have a virtual address space allocator, primary role passing, as we mentioned. So it's like we can do device reinitialization. When a process dies and comes back again, then we want to attach to the same device, because we don't want to reroute traffic. Okay, so we're providing a simple memory management API for our application. So it's very simple. It's just a named memory partition. So every application can attach to its memory partitions. Like the process just says that I want to connect to my private memory, which is previously set up by a name in the configuration. So it can get to, every process can just get to the closest possible memory partition. Yeah, and we provide flexible configuration and reconfiguration without changing the code. So it's like you can just switch from 2 meg to 1G, or so it's like 2M huge pages to 1G, or even 4K, or you can change the size of a given partition. So yeah, so that's how we made DPDK NUMA aware in the NUMA flat OS. So it's like we are presenting a virtualized world to DPDK, and then we show the old topology. And we also gained a more granular way of placing objects. It's to control the TLB entries, and even we can get 0 TLB miss. So it's like every instance can get a 4G 0 TLB miss memory just by aligning it in the right way on a Xeon processor, because we have 4 slots there.
How is it that you map the virtual memory that you're given to socket local memory?
Yeah, sure. Okay. So actually, this is how. I mean, this is what we did. So so this is the summary of the previous one, and I can explain all these slides. So it's like we have the DPDK memory. So let's say in this example, we only have 1G huge pages here. So it's like these are the huge pages, and DPDK memory, DPDK says it has a contiguous in optimal case. So it's like when we start up two processes, and mem zones can, I think since DPDK 1.3, mem zones can be in a multiprocess environment. Certain processes can even create mem zones. So it's like if you start up two processes at the same time, and they are on a lock contention, so each of them, they will allocate their memory, so your memory gets quite fragmented. And this is our mapping. So with our mapping, we can make sure that every process, so it's like if this is the private memory of the process, of this process, and that's the private memory of the other process, we make sure that it's always using its own DPDK sockets. So actually, these are the DPDK sockets, and this is the trick we did on DPDK. So it's like we made DPDK a multi-socket version. So it's like even on a single socket machine, DPDK will see multiple sockets. So every core, every L core can have its own dedicated DPDK socket. And this way, for example, even the RTE malloc can work always from its own private memory of a process. So this way we can get even 0 TLB miss on a per. Yeah, data. Yeah, I'm talking about purely data TLB miss now. But even instruction TLB, that's another topic, I guess. Okay, so so this way we're actually partitioning the memory, so we're showing DPDK multiple DPDK sockets, and it cannot just be one DPDK socket per L core. It can be multiple depending on the configuration. So fragmentation support. This is something we put on top of the mem zone allocator, so we can allocate multiple mem zones and stitch together to a virtually contiguous space. And per L core private memory, I was talking about that. Yeah, and still we haven't touched DPDK, so the trick was actually this DPDK socket. DPDK has a memory allocation already, so the goal was not to touch that deeply. Yeah, okay, so we have a kind of resource manager which always keeps track of the available resources like the L core, CPU, memory port, queue devices, and we can even provide on-demand devices to DPDKs, like like a pop-up interface or something, pop-up. And it also gives us the possibility to reclaim resources when a process dies and comes back again. Then we can, I don't know why.
Can you move your microphone down, dude, with your shirt?
Yeah.
Somewhere in the center.
Okay,
Is that better?
can you hear me? Okay.
Probably try to put it right in the center if you can.
Okay,
Test.
probably.
Is that better?
Is it okay now? It's fine? Okay, good. Okay, so actually, we can reclaim resources like previous ports which was used by an application, or even a shared memory which was used by the application, or a private memory. And we provide, our infra provides a way to configure, so to use ready-to-use configuration. So it means that we can publish a configuration of an application, so like the memory partitions in advance, and the mem zones, we call it as mem domains. So actually, we're not directly giving the application to reallocate allocate mem zones. We're our configuration is a kind of an abstract way. I will show that later on how we do that. So it's named packet pools. We provide named packet pools, so that gives us the possibility to just update the number of packets within within a packet pool. So application just wants to connect to its named packet pool, and then it gets the handle, and it can allocate packets from that. And it's up to its configuration, which is offline or maybe dynamically. Okay. And it's the same for the virtual ports queues. So at the end, actually, everything is just a resource. So it's a pool of resource. So it's like, I mean, that's how it looks like. I should stand here. Okay, so actually, when the application comes up, it requests for an L-core, and we decouple the L-core usage from the CPUs. So it's not strictly connected. An L-core is not strictly connected to an L-core or to a CPU. And actually, then we will pick one execution unit for it, one HD in this case. It also depends on the application, the policy. And so this HD belongs to this socket. So then when the application says that I want to connect to my exclusive memory, we know that this instance runs on this partition, so we assign the right exclusive partition to it from the right socket, and also the NUMA. So NUMA is something which every process can connect to. So it is useful for us, for example, for the forwarding tables, read-only. Is there a question on?
Question on the bridge.
Yeah.
Can you explain a little bit more about how packet pools are tied to the ports?
How packet pools are tied to ports? Okay, yeah, actually we have something called packet domain as well. So we have a kind, I mean, that's also, that should be, would be another presentation, I guess. But so this is something, we call it virtual ports, virtual queues. So the application describes the queue, the port. It's also a named port and its requirement. So within our configuration, we have that named port, and then the application can connect it to a packet pool, which was already configured in another section. I hope it answers the question. I don't want to go into details because we don't have so much time, I guess. How much time we have?
We've got about 40 minutes, 45 minutes, so you're fine.
Ah, we're good. Okay, yeah, so I can talk about
We're running ahead a little bit, so we're good.
Okay, so good. Yeah, so actually this is how, I mean, then the application can request to attach to the default, and default is something, I mean, these are all named partitions, so it doesn't mean that the application can only have a single exclusive partition or single NUMA. They can configure as much as they like. And actually default is a normal shared memory, so everyone can connect to it. And in this default type, we usually don't care if it's which socket it is. And in the NUMA-wise, it's also, I mean, I started to explain it. So in the NUMA-wise, for example, for the FIP tables, it's very useful because we map the NUMA as read-only. And there's another user, there's our controller, the background process, which attaches to both of the NUMA, because we also give the possibility for the application so they can connect by index to all NUMA partitions, and they can publish. So it's like the publisher part can use, can map the NUMA memories as read-write, so it can maintain the FIP table, the forwarding table, and then when the application attaches to this, then it doesn't care if it comes from this NUMA or that NUMA, and it doesn't want to know. It just wants to get to a quick, the quickest memory partition. And since we know where it is running, we know where to attach. So yeah, it's the same for the ports. So it's like we want, if we use SRIOV, we want the ports to be coming from the same NUMA socket. Also for software queues, it's valid. So these could be even virtual ports, which I mentioned here. So it's like the application doesn't tell us to connect to this PCI device or this DPDK port. It usually just tells us the name. So it just tells us that I want to connect to my front panel port, and then we pick the port from the right socket if we have multiple configured, and then we pick the right queues for them. So it's like if it's another application, another L-core, it can connect to another port. It's actually, the name it could be the same, but it may connect to another port, and then we pick another queues for them, which could even be some software queue. So the application doesn't have to know.
But you generally have an abstraction layer between physical devices, received queues, created queues, and the apps queues?
Yeah. A very thin layer we have. Yes.
So you've got somebody in there then that's
Yeah, that's right.
queues other than the app itself.
Yeah, and we have our own APIs, our packet socket APIs.
Hey, I have a question.
Yeah.
Probably it's similar to what the other person was asking. On the NIC interface, when we receive packets, are all the processes memory mapped directly to the packet pool so that everyone has read-write access, or do you have an abstraction layer where you copy the packets into the processor's memory?
Can you repeat the question?
Yeah. So the question was if all the instances has access to the packet pools, or if I understood right. So actually it depends on the application model. So if the application model is like every instance is just receiving packets, it's a run to completion model, when every instance is just receiving packets and then sending them out and no interaction to the other processes at all. In that case, it could be a private, and that's more efficient usually. So it's like you just want to partition, so you just want to slice your traffic, and multiple instances are handling certain slices of the traffic. In that case, you don't need the packet buffers to be mapped to other processes. So it depends on the application model, which the application can describe in its configuration. So if it wants to pass packets in between, or do it in a pipeline model, in that case the packets are mapped to all the application, all the processes space, whoever is using. So we also provide a way, that's the thing I mentioned, we call it packet domains, where the application can just attach to its port, and that's the way we know that we also have to map the packet buffers associated with that.
In all these things, right, what is the movement? What kind of, for instance, do you dynamically add in L cores, do you dynamically add in NUMA zones, and dynamically unplug L cores and NUMA zones?
So am I understand right? Is it the question is that if we dynamically add these packet pools, or we just statically?
CPU L cores, NUMA zones, you actually dynamically add and remove them, and you dynamically add them.
If you can do this dynamically, that's the question. For now, we don't have the support for that yet. So actually, at the moment, we're just allocating statically all these L cores. So we just, based on the configuration, we derive the resource need of an application, and we connect them together. So at the time, so actually we just pick the right L core, and then all these resources, which was described in a configuration, is allocated. But it's like, if the application wants to change something, like increase the size of the exclusive or add one more memory partition, then it just have to extend its configuration file, and then it can get access. Or I mean, we can increase the size of the exclusive, or we can try what happens if I put the exclusive on 1G and put the NUMA on 2M, just by changing the configuration. So, does that answer the question? Okay, but we are planning this pop-up, even pop-up NUMA, pop-up CPUs, or claim the resources at the time of when we get the request from the application.
So after you reconfigure, do you need to restart the process?
Yes, at the moment we need. Yeah. But we can, I mean, we can simply extend it to, for example, to add more MEM zones, because that's. So we cannot delete or cannot remove MEM zones at the moment in DPDK, but we can extend to create new partition MEM zones. That would be simple. But we have the plan to support, and that's actually the multiple DPDK socket model supports us. So it's like you can completely clean up a full DPDK socket, which belongs to probably. So actually, if it's a run to completion model, it is easy that one L core, so all the resources, all the associated queues and everything, all the mem zones belonging to a particular L core is on a single DPDK socket or multiple DPDK sockets, but we know that this is private to that L core, so we can just clean up the whole DPDK socket. Okay, so does that work? Ah, yeah, okay. So this is how we pick. I mean, if we pick another hyperthread, then we assign the resources from the other NUMA socket.
So, question about port, picking the port. How do you know the association between ports and sockets? What do you rely on?
Yeah, actually, that's the publisher. So that's why we said that we decouple the EL layer, so we publish the port information, and actually so that's a kind of whitelisting devices, and also the additional parameters are part of our attribute tree. So it's like we list all the devices, the virtual functions, if we use SRIOV, and then we have, so it's like all the parameters like the NUMA socket and the physical functions. So if we have 4 ports, so actually we might have 4 ports, two per socket, and in that case you also want to do load balancing. So that's the task of the resource manager, so that when this process picks one port, so maybe if I mean this guy comes up, then we pick a port, we pick port 0, which is also on socket 0. But if this guy comes up, then we pick port 1 just to load balance. And it could be
It's a manual config. It's a manual act to create this whitelist of port configs.
No, it's not a manual config. It's in our case, we have a publisher piece also living inside another VM, which actually they are communicating to each other. And then that's where we get the information. So that also has the connection to the hypervisor layer.
That's what I was saying. Ultimately, the source of truth is your platform. Right?
Yeah. So we need a kind of source, but it could even be detect. So auto detect. So it's like you can detect the topology if you know that the VM is not using ballooning, but you can detect the environment as well. So that's how we made it flexible and adapting to the environment.
Sorry, so basically the BIOS and ACPI tables are the ones used there.
No, actually, we are not using the ACPI. I mean, that's what is missing from Zen. So the ACPI is not published by Zen, and then but then we need an additional info to get the topology. If you're running natively, because we can even run natively, so this whole stuff can run natively. In that case, we use the standard Linux interface to detect the NUMA topology and publish it that way. And also it gives us the possibility to simulate. So it's like if you only have a single CPU, you can simulate 4 socket and 64 vCPUs as well.
So, but what you are saying is that you have this publishing as part of hypervisor now, because you need to discover the topology from there.
Yeah, we need to discover the topology. That's
maybe I missed it. This is a single DPDK process, or can you have multiple DPDK processes?
You can have multiple DPDK processes, yeah. So we are running in a multi-process, but we also support the multi-threaded model. So it's like we have an L-core assign. We introduced an L-core assign API. So the application just tells us the name and L-core assign and certain parameters, flags. And the name can already be configured in a configuration. I mean, what resources it requires, or it can so it can be based on the application how they want to use. Okay, so yeah, it's just putting some results on how it looks like. So it's like our test application is just first attaches to a memory area, which is our private. In this case, it was a private memory partition. So it just simply tells us attach to my private memory, and then we get to, based on the configuration, it could be different, and we did different tests. So it's like then we fill up the area with random. So actually it's randomly chained data, so it's like you're jumping through the memory. And we wanted to control it by a packet. So it's like we receive a packet, and then Then we do multiple reads and writes, which is configurable based on our tests. I think we did 5 writes and 10 reads in this case. And then we just send out the packet. So we just touch the packet. So actually within this test, the packet content is not manipulated heavily. It's just like we swap the IP and attach some metadata to it and add an additional header. So it's just a simple packet function. In this test, we more wanted to test the memory. I mean, what we gained with this NUMA and what we gained with this whole infrastructure. Okay, so this is how it looks like when you bring up a DPDK in a Zen virtual machine. So in this case, it's the memory allocated underneath when your VM is span across 2 VMs. In that case, it looks like these could be the 1G huge pages actually. So this is socket 1 or socket 0, socket 1, and then the huge pages are mapped like usually this is 1G on one socket, 1G on other socket, and we have the MMIO holes which we take care because those will be mapped by using 2M huge pages. And
what was that last part? Sorry.
Which one?
The part about we map them to 2M.
It's actually that you cannot give. So if when you ask the hypervisor to map all the VMs memory space with 1G huge pages, the first half, and so there are some holes there. Yeah, which you have to reserve. So in that case, so you cannot just pass. You cannot back up the whole VM's memory with 1G huge pages. So if you want to use really 1G huge pages, that's another trick because it's very important to reach the 0 TLB is that you need to have 1G huge pages inside the VM, which is actually just the guest physical memory, and you need to have 1G huge pages on the extended page table layer, which is another layer on top of DPDK's virtualization technique. So, is it going? I don't know what happened. No. Okay. Yeah. Okay. Yeah. So okay. So in this case, we don't want to put some numbers on it, so we just show it like this. So we get one performance like this. No, it doesn't work. Yeah. Okay. And this is how it looks like when we put our infra on top. So it's like in this case, everything will be aligned. So if we want to allocate, if this is the process's memory, it just allocates everything on a socket 0. So it's like if you do memzone alloc, then in DPDK you get this kind of pattern. So 1G in one socket, 1G on another socket, and this is our memory layout. And then we got 53% improvement just by making. I mean, it's actually it depends on the application always. So you cannot say that every application gains 50% performance just by putting them on the right NUMA. It's not true. I mean, it always depends on the application how it accesses the memory. So in this case, it's actually the packet. So if you put the packets on 2M or 4K, it doesn't matter usually, because in this case the more access is the random access is what is more important. So yeah, so this is the single socket 0 TLB miss. So how we reached and what we gained with this 0 TLB miss. So actually this is the fragmented behavior, and this is our mapping. So it's like these are the 4 1G huge pages. So we wanted to check what happens if we use 4 or more TLB misses or TLBs, and actually we gained 60% here, which seems to be low, but there are other factors as well. So it also depends on the application, and what we gained is a deterministic way. So it's like when you send a packet, it goes through randomly, it reads through the memory. So in that case, the packet delay variation can be quite big. So it's like, depending on where the memory page is, which the application is accessing, it can highly vary, because TLB miss is particularly costly in a VM environment. So we need, I mean, because we have the external, the extended page table on top, so it's more costly than in a non-VM, and actually that's what we optimize for. But it requires the hypervisor to also provide us a way of, so it's like we should be able to ask the hypervisor to put our pages on 1G huge pages.
On that 16% improvement, does that directly correlate to the number of TLB misses eliminated?
No, actually, that's. I mean, as I said, it always depends on the application. So in this case,
for this benchmark, though,
for this benchmark
was 16%.
Yes.
So was that directly a result of the TLB misses?
Yes, yeah, that's right. So it's the only thing was. So we did actually so it was not fragmented like this. So what we did was 512 meg in a DPDK memory. So we allocated 512 meg for one process, other process here. So it was in a kind of a pattern. So in this case, we used 8 1G huge pages, and in that case, we used only 4 1G huge pages per process. So that's the 16 process. That's where the 16% comes. And also, we see the stabilization of so it was very stabilized. And also, our applications can see this stabilization. So all instances are running at the same even. Yes, Mati.
So the previous slide was that you showed, like, was it like this one process and this is two processes?
Yeah, actually, the previous one was that was just one process, and this is two processes.
So Laszlo, did you ever try this experiment with 2 meg pages?
Yeah, we have measurements even for 2M pages. I don't know. Do you remember what was the?
The performance is generally less, right?
No, it depends. It really depends.
Oh, yeah.
So. Okay, so it looks like in every application of ours, we had to try to turn your mic back on and the key turn it down. All right. Okay. So the situation was that we had to come up with this flexible configuration environment, because it looks like every single application is different in terms of bottlenecks. And when first time we have learned about the 1G pages, oh, what a good idea, yeah, we must use them. And it looks like in some cases, some applications performance went down with just forcing them to go on 1G pages. And that's why we had to do some checks. What happens in case of one packet? What is the memory read and write on a packet base? And that's why we have this configurable environment where we can decide what type of memory during the packet processing to put to 2M pages and what type to go to 1G pages. When we cannot stick really much within the 1G pages, 2M pages used to be better. So if we're talking about 10G of memory, it looks like if we put them on 2M pages, they perform better. But if we're pretty close to the 4G, 5 and even sometimes 6, that's better for using 1G pages then.
But this is actually depending on the application. I mean, it's always, as I said, it depends on the application usage, and that's what the good thing in this stuff is that if you can tune it for your application. So it's like if you want to, so you can try what happens if I put only my packet buffers on 1G huge pages just by changing the config and change your allocation to 1G. You can even put the packet buffers on a mixed. So you can even create a mixed 1G and 2M partition for your application. So you can try what happens if I only allocate 4 gig on 1G huge pages and the rest on 2M huge pages. And if you have the control by the application to allocate in this certain, so you can say you can create a fast memory, you can create a slower memory, and you can create a slow memory, and then you can configure it in that way. So you can have 4G of per instance or per socket memory, and then, but it's always the configuration, and you can extend your memory allocator to to be able to allocate from a given partition.
And we could also play with cross-NUMA tests. It means that only by changing the configuration files, we could check. So we could check all the cases when, let's say, the interface, the physical interface, let's say it's an INTIC is on one socket, we have the CPU on the other socket. So it means that the packets go to the L3 cache through the QPI, and again, the process's memory allocated on the other socket again. So we could check even these configurations by just these setups by just changing the configuration file.
Actually, this is also, I mean, this test was also, we wrote the code once and then just play with the configuration. So this is also just something which, a single switch. So we just switch, we have a switch to force NUMA or force a single socket, and then in that case it's your allocation will be going back to the DPDK allocator in his environment.
So just one last question about that. How many 1 gig TLBs in this setup that you have on this processor?
Or the hardware? Four per physical core.
Four, yeah.
Okay. Do you notice any L1 cache, L2 cache affects the size of whether that size the degree of performance, the L1 size of the L1 cache?
So what was the question?
The size of the L1
Mm.
a bigger cache improve your performance, or did you notice any variance?
Actually, we haven't made such tests here, so you can do plenty of tests with these. I mean, the good thing is that you just need to reconfigure or configure. We can even, I mean, we have plans to use cache QoS, where you can control your cache. So you can even create a mem domain, a fast memory, where which is using cache QoS. But we need to experiment with those things.
But it looks like we really need in the L3 cache, because that gives us the best performance. So that's why Laszlo said that we want to make use of the cache QoS if it's possible, because we came actually from the packet processing area with special packet processing chips, and we get used to the luxury that we can configure the memory the way we want, and we always know what is in the memory and where is that. And as the x86, the Xeon processors are more like generic processors. They have really fantastic prefetch algorithms, and they are learning, and they do all the generic stuff really well. But packet processing is not generic. And in that case, we still think that we might have some serious performance improvement if we can control the cache itself.
In what cases 2 megabytes GPU size will give performance comparing to use 1 gig memory huge page size?
I think it may depend on the number of pages. So it's like if you receive a packet and you have, for example, 5 1G huge pages, and for each packet you have to jump through different. I mean, you are jumping through 5 and maybe jumping back to another huge page. So it's like you always. So at a single packet, you might access only certain portions of the memory which are in different 1G huge pages. And then if you jump through them, you go out of the 4 1G limits. So while you're jumping, you go out of the 4 TLB limits. But if you are doing it on a 2M, then you have more slots for 2M. I guess 64, we have 32 2M huge pages. And then in that case, you might just jump through the ones which, so I don't know exactly. I mean, we just have guesses, but maybe someone knows better if, but we just have ideas on what could happen. But we heard that many times from our applications that they run better with 2M huge pages than 1G huge pages.
So it ultimately depends on your replacement rate.
Yes, yeah, that's
so what
what we.
happens with 1 gig is you've got 4 of them, and you can always continuously hit a miss on the next data you're accessing if you're straddling across 4 gig, 6 gig, and that's kind of what you see, right?
Yes.
At 6 gig, it seems to be okay because about a 1:1.5 oversubscription. When you start going beyond that, you will end up with situations where you have essentially a replacement every time you do a read. And that's what causes problems. So the reason I was interested in the question I was asking is, if you've done experiments with 2 meg versus 1 gig, you have a very flexible system where you could map things into 2 meg or 1 gig depending on performance boundaries or performance. Let's just put it like this. You could probe dynamically cache misses or TLD misses. You could actually move mappings around to go figure out what your optimal mapping is for an application. Have you thought about things like that?
Yeah, actually we were talking about, but I mean, we thought about that, but that's it's not yet done, and we guys work. So there are lots of, I mean, we have lots of ideas what to do, and yeah, you can even do some kind of an auto detect mechanism to detect your patterns, and then you can tune up your config for that.
That's what we've seen. We've seen a lot of applications that benefit from certain selective mapping into 2 gig, certain into 1 gig. Optimize the pattern across each one.
Yeah, right.
So that's why we suggest to the application. That's why we suggest to the application to use the 1G pages, and probably only 4 of them. So if they have the really sensitive data, which is accessed pretty much frequently, a couple of times per packet, we suggest to use them, the 1G pages. And if they can really configure their amount of data to remain within the 4G border, then it's going to be really fast.
So it's even better to extend the application to be able to allocate fast memory and slower, as we said, and in that case the application can control the allocations. Okay, so I don't know if we have, I guess we ran out of time now.
We'll give you 5 minutes.
Okay, yeah, so actually, so this is, I mean, this is the test results which we gained by putting both the 0TLV miss and the NUMA under Zen. So this is, we gained 77% improvement on this particular test, and that's important because it depends always on the application, as we said. So
and it's also, we already have all the tricks we used to know. It means that we have pin CPUs, we have shielded kernel stuff, we all have the IRQs sent down to one CPU and things like that. So basically, in case of the packet processing, the special packet processing CPUs, we really can have only the packet processing code running on a single core, and we try to model that on an x86.
Be aware of the NUMA or beware of the NUMA. So it's usually better to put your VM on a single NUMA system, and I think that's the common technique. But if you need a spanned one, then you need to be aware of the NUMA allocation.
To open source this infrastructure?
Yeah, we expected that question. So yeah, we. Yeah, so actually we need to, I mean, Ericsson is a big company, so there are certain policies, but we're planning to contribute, so hopefully we get a, yeah.
At least here we are with the idea.
Yeah. So.
It's not.
No, yeah, we came
how this one is different than the packet framework process, which is basically the DPDK concept.
The concept, I guess, it's...
What you are now playing is basically the IEAL configuration, right? That's all what you're considering in our case.
So actually our packet domain, what we mentioned, is somewhat similar to the same concepts are the same. Actually, it's just that, I mean, we had no packet framework when we started the work. So, yeah. Okay, so yeah, huge page packing is also important on the hypervisor side, so we need some control for the hypervisor. The LV misses could be costly or more costly because all these tests were done in VM. We made no native. I mean, it would be interesting to see what happens in native, but okay. So yeah, proper memory alignment is vital, and these are the ideas which we can still do. So it's like yeah. So we can improve man-zone allocation. So we have lots of ideas, and this should be, can improve it further. Yeah.
Can you talk at all about, for like, I don't know, 45 seconds about this abstraction layer
One of the bigger problems I've had with the DPDK is getting the work distribution right. You just have one core services, one queue or two queues.
Yeah.
You use RSS if you have a non-power of two number of cores or queues. So you said you had an abstraction layer, like
yes.
There's a one or two queues you're burning to do just RX, and then they're distributing off to the application queues. Can you talk about
that? Yeah. Actually, we have a we have an example of. We have some backup slides on at the end. Yeah, so it's like, this is our configuration example. In this case, the application just configures the foreground mask, which could be, any. So it's like similar to the CPU sets in Linux. They just configure the foreground mask. It tells us where it wants to run their instances. So we can also pin their instances to those. And then our configuration. So this is our memory configuration. Actually, this is not the packet domain. I think we don't have the one in the packet domain, but so it's like in this case, it just tells us the type NUMA, where it wants to run, and if we want to allocate mem zone for this. And so this is kind of an abstraction. So it's like if they it more. Oh, sorry. Yeah, it's this is one. So in this case, the foreground has only few bits. So if we know if the application sets up like 16 CPUs in the foreground mask, then we know that we need to create 16 exclusive mem domains, exclusive memory partitions. So it's like just by changing the foreground mask, we enable one more instance to come up. And that's the same concept or similar concept for the packet domain. So it's like it's also there. They create virtual ports. So what they see is probably a DPDK port. So it's like they can set up the ID. So they create like the front panel port, and they say the ID is 0, and I want to have queues for each of my foregrounds. So it just tells us the CPU alias. So I want RxTX queue pairs for one for within this virtual port, and it can describe more. So it can describe some attributes. What is the requirement for this particular port. And when it wants to connect, it just tells us I want to connect to my front panel. And if we are running on an SRIOV system, on a system where you have each foreground will get a dedicated virtual function or a dedicated RxTX queue pair, then we just assign a PCI device for each of these for every processes. But if we are running on a system which only has one port, a VirtIO port maybe, and one RxTX queue pair, then that port, the front panel port, could even be a software queue. So behind there is a software queue in that case. The application doesn't have to know. The application just pulls packet out and sends packet to these queues. So it's just named. So that's what it's the named resource pool.
But if you're burning a core to do just RX queue processing, for instance, right? It has to pull the packet in, and it's going to give it to one of the applications. It's going to have to touch the packet by looking at like the first 64 bytes or whatever. Can that keep up with the high line rate?
It does.
One core?
Yeah, usually it does, but it also, you need to decide. So that's the application model. So we may have VirtIOs per socket, or we have, that's something which is the platform's. So we are a platform, and the application doesn't have to know about that if we need to burn so much code. So it can even be an IVSHM. So it's like it could be a shared memory software queue, and the resources will not belong to the application. So we do not burn the CPU of a certain application. We may burn a CPU in our VM. We may need another VM, but yeah. Okay, sorry. We're done.
Laszlo and Andras. Thank you, guys. Thank you.